Hello, this is our final for MMAE 445. We're the spray bottle group. My name is Richard Stubing. My partners were Max Romanelli, Kenton Scheel, Michael Lenardi, and James Holden. So for our project, we worked on a spray bottle. So on the left, you can see the picture of the spray bottle. Material is ABS plastic. Material properties are it's a 2,000 Newton per millimeter squared Young's modulus and a Poisson's ratio of 0.394. To the right, we have the 3D model that we created of it. We'll go through some of the parts that make up the piece. Here we have the sprayer head. This is the biggest molded part on the project. It's injection molded, has several points of stress where the forces are applied, so we'll be doing an analysis on this. Over here we have some of the smaller parts that go into the project. We have some of the caps, the spray caps, the spring holders, triggers, etc. Here we have the squeeze handle. It's another part that will be a major focus of the analysis due to the fact that the major forces will be applied to it. We have the pin and cap here, so this is the point of pivot from the squeeze handle to the sprayer head. We're going to be doing an analysis on this piece as well because it's a major failure point that we want to make sure works as well as possible. So this is the total assembly once again of the sprayer. Here we have the forces that are exerted on the the spray nozzle head. You can see that at the pin joint there is forces from the squeeze handle as well as from the supports of the spray head. And then on the right side you can see some more of the forces being applied. There are several moments. We find that in our analysis that the average force applied is about 8 pounds or 35 newtons. That's the force needed to complete the motion of squeezing the handle. To the right we have the meshing of the pin, so we'll be doing the pin analysis first. Here is the pin analysis. Once again, we have the loading, the constraints, and the loads. You can see those. When we first ran the analysis, we used the expected weight or expected loading from our calculations, so 8 pounds or 35 newtons. That turned out to be pretty light. We didn't see very much results, didn't see much deformation. There was really no deformation or stress concentrations because the loading was so light. So we ramped it up a bit, used some higher loads, and we got some deformations so that we can prepare for the future. Here we have the stress strain curve on the left for the ABS plastic. So you can see that we were operating in the about 8 megapascal range, so well below the yield point of around 26 megapascals for the ABS plastic, which is the solid line because it was injection molded. On the right we have the SN curve, so the number of cycles to failure. Once again, we're operating in the range of about 3,000 to 12,000 cycles to failure for our operating range. So relatively high amount of cycles to failure for this material, which is why we had to under the loading that is normally applied. So that's why we had to ramp up the loading so that we can see some better results. So here is the deformation at a much greater loading. You can see on the right that they're relatively significant loading considering this is a pin. We really can't afford for much loading at all. On the left side you can see the stress concentrations from the loading. Here we go. So for the changes we decided to make, we couldn't really make too much design change to the actual pin. Normally we would try and make the area a little bit bigger, add more volume, more material. We didn't have room to do that because of our design constraints, so we decided that the best way if the deformation was an issue would be to change the material of the pin. So here we decided to go from the ABS plastic to aluminum. The aluminum has a Young's modulus of 69,000 newtons per millimeter squared, so significantly greater. You can see on the right side that there was significantly less deformation, really no deformation at all. So if that were a problem, that would be a solution that we could try and use, just improving using a stronger material. Up next we have the squeeze handle. You can see that this is the loading under the normal squeeze handle. So On the left side, the loading applied over the squeeze handle. The constraints were about at the pin joint and where it comes into contact with the spray nozzle. On the right side, you can see the stress concentrations. There was a significant stress concentration right around where the ridges are for the hole where the spray nozzle would normally come out. So that's right around here in this area. So some solutions that we came up with to fix this project, or to fix this piece, we could add some ribs into the spray handle because it's hollow underneath. So that would be one solution. Another solution would be to rounding out the ridges to add a little more material and more evenly distribute the stresses. So as we can see, so here are the suggested changes: the ribs on the left side, and then we have the rounding up here on the right side. So then we'll see how that worked. On the left side, you can see the meshing. We had to go with the very high amount of nodes because of the unique geometry of the ridges and then the added rounding. So unfortunately, we were not able to run the analysis because we have a maximum value of amount of nodes allowed for the license that we have on this on the Abacus CAE. But however, we can assume from other pieces that we have added ribbing to and from past experience that these would assist in distributing the stress more evenly. So up next we have the sprayer head, the big piece here. Forces applied are on the left. You can see over here that the pin joint area is a major loading point. On the right side we have meshing. So results of the initial analysis we have, you can see that there was significant deformation in the pin joint, and then we also have some deformation in the head of the sprayer. So those are some pieces that we're going to want to fix. This once again was with a much greater loading because under the normal loading conditions there was no deformation or significant stress concentrations that we noticed. So we used much higher load to see some deformation. Some of the suggested fixes here, we have to add these ribbings in near the pin joint head. So we were hoping that those would assist in limiting the deformation. And then another possible solution to the deformation of the pin joint would be to add an aluminum insert. That would actually serve two functions. So it would add rigidity to the pin head, so make that area stronger, less likely to deform. Could also add in some lubrication, so lower coefficient of friction allows to easier squeezing of the handle. So we ran the analysis, and we can see from over here on the right that the ribs succeeded in limiting the amount of deformation in the head. There was still deformation in the pin joint because the aluminum was not applied. However, we can assume that would be a sufficient fix for the issue. So that's the analysis we ran on our project. Some solutions we came up with to make this a better product and to show off our CAE Abacus skills, SolidWorks skills that we learned throughout the semester. So thank you very much.